Hi, hello. My name is Muhammad Ali from Mechanical Engineering. My tech talk topic on film simulation of temperature field during laser forming of sheet metal. Subject: finite element analysis. Film simulation of tech temperature field during laser forming of sheet metal, and in depth how laser energy transforms sheet metal, focusing on the crucial role of thermal modeling. Introduction to laser forming principles and industrial applications. Laser timing is a flexible and non-contact sheet metal sharpening technique that uses a focused laser beam to introduce controlled plastic deformation. Unlike traditional methods that rely on mechanical forces, laser forming leverages thermal stresses. When a laser beam scans across a metal sheet, it hits a localized zone, causing thermal expansion. As this heated zone cools, it contracts, leading to permanent blending or curving of the material. This process is particularly valuable for complex geometry, small batch. Right. This is the temperature gradient mechanism, buckling mechanism, upsetting mechanism, non-contact process, high precision, material versatility, reduced spring back, localized forming. Significance of temperature field in laser forming process. Direct driver of field directly detects the thermal stresses and strains induced in the material. Uneven heating and cooling across the sheets thickness and width create precise thermal gradients, which are the fundamental forces causing the plastic deformation. Without control temperature variations, laser forming would not be possible. Control over bending, width and duration of the heat zone, all governed by the temperature field, directly correlate with the achieved bending angle and radius. Precise control over the laser parameters influence on material and prevention of defects. These are the overall efficiency of the process, making thermal analysis an indispensable part of process design and optimization. Fundamentals of finite element method for analysis, thermal analysis. Key concepts of FEM for heat transfer, discretization, meshing, governing equations, and element formulation, assembly of global system, boundary conditions, solution and post processing. FEM provides a robust framework for simulating the complex and transient heat transfer phenomena involved in laser forming, accounting for temperature dependent material properties and various boundary conditions. FEM model on development, geometry, material properties, and meshing strategies. In this FEM model for laser forming involves meticulous definition of geometry, precise assignment of material properties, and strategic meshing. Geometry definition. The first step is to create a precise 3D CAD model of the sheet metal workpiece. This should be accurately represent the dimensions, width, thickness, and any pre-existing features for laser forming. A simplified 2D plane strain or plane stress model can sometimes be used for preliminary analysis if the bending is in one direction. However, for complex paths of multi-process forming, material properties. Accurate material data is critical since thermal and mechanical properties of metals change significantly with temperature. Key properties key required include thermal conductivity, specific heat capacity, density, coefficient of thermal expansion, yield strength, and Young's modulus. In meshing strategies, refined machine critical regions and element type and transition to coarser mesh quality also. Simulation results transient temperature field and thermal gradients. In this provides the dynamic time dependent transient view of the temperature distribution within the sheet metal during and after laser laser heating detailed thermal field is crucial for understanding their induced stresses and subsequent deformation. Laser heating phase, heat conduction and diffusion, cooling phase, receding temperature and stress. Analysis of parameter influence on temperature distribution. Laser power was impact, scan speed MMS and beam diameter and number of scans material thickness. In the sensitivity of various process parameters which directly influence the transient temperature field and consequently the final shape frame simulators enable to systematic analysis how these parameters affect the thermal distribution. Practical implications, process optimization and distortion. Process parameter allow engineers to virtually experiment with different laser powers, scan speeds, beam diameters, and scan patterns by observing the simulated temperatures fields. They can identify the optimal combination of parameters to achieve the desired bending angle of shape with maximum efficiency and minimum energy consumption. They reduces for need for costly and time-consuming physical initial or error experiments. Distortion, prediction, and control. Global warming, bucking, and localization is a common challenge. Is laser processing the temperature field simulation coupled with a subsequent mechanical analysis can accurately predict these distortions by understanding the thermal history. Engineers can them devise strategies to mitigate them. This might involve optimized scan strategies, pre-compensation, cooling control, improved product quality, and furniture. The temperature field frame simulations ensure that the materials, microstructure, and mechanical properties are not adversely affected. The prevents issues like excessive grain growth, embitment, or surface degradation, leading to higher quality components with consistent mechanical performance and increased fatigue life. This is particularly official and high performance applications and aerospace medical industries where material and conclusion. Key findings and future research directions. Key findings: temperature field is the core simulation inequally demonstrates that the transient temperature field and its sleep gradients are the fundamental mechanisms dedicated to plastic deformation in laser formatting. Parametric sensitivity process parameters such as laser power, scan speed, beam diameter, material properties exert a significant influence on the temperature distribution, directly affecting the bending angle and final shape. Predictive power of frame the provides a robust, accurate computational framework basis of optimization. Understanding in the temperature field is crucial for optimizing laser forming parameter, controlling unwanted distortion, and ensuring the mechanical integrity of the formed components. Future research directions: multi-physics coupling, integrating thermal, mechanical, and metallurgical phenomena more comprehensively to account for phase transformations and microstructure evolution during rapid heating and cooling. Machine learning integration, developing data-driven models that leverage simulation data to predict optimal parameters and control strategies in real time. Hybrid laser forming process and investigating the temperature field in hybrid processes that combine laser heating with mechanical deformation. Advanced material modeling incorporating more complex material constitutive Models that capture an anisotropic behavior, strain rate dependency, and damage evolution and high temperatures. Experimental validation and calibration for the experimental validation of temperature field predictions using advanced measurement techniques, real-time process control, developing closed-loop control systems, and these temperature measurements and predictive time models. Thank you.